Okay, so, last time I joked, like, now we can really start 162. And jokes aside, it's kind of true. Because everything before was review. That doesn't mean it wasn't important, of course. But it was just getting us up to speed, getting, re-remembering classes and whatnot, and of course, familiarizing ourselves with Java. And then I kind of mentioned some of these data structures. We talked about stacks, right? Queues, bags, trees, graphs. And the ones we're going to cover are stacks, queues, bags, and trees. We're not going to touch graphs actually in this course. And all of these data structures have different pros and cons. And they all kind of serve a specific purpose. Like, remember going back to 161, right? Like, there were lists, right? Lists are great. Lists are remarkably general purpose. But you might also remember from 161, we had sets, right? Remember we talked about sets? We also had dictionaries, but let's think of sets. Sets are kind of like lists, but it'll only ever allow you to have one version of each thing in it, right? No duplicates allowed. And you might say, like, a naive person might say, like, well, why would I ever really want a set? I could just use a list, right? A list is far more general, and you're right. But you use a set when you need a set. Because that time you want data to be no duplicates allowed, and you want all the properties of a set, you use a set. So although there are more general purpose things, you use the right tool for the job, and sometimes a specific tool is an amazing thing for a job. And like the first one we're really going to cover is stacks. And a stack is great for maze solving, which is assignment 2 and assignment 3. But another thing computer scientists are obsessed with doing. This is a common theme you'll see if you carry on taking more computer science courses. We're obsessed with, like, finding out what we can do with a very limited amount of things. Like, we're going to learn about a stack, and a stack is far more specialized and not as general purpose as something like a list. But computer scientists are obsessed with going like, okay, but what can we do with a stack? Like, what problems can we solve with a stack effectively? And someone can say, yeah, but a list is far more general. And they're going to go like, yeah, who cares? But what can we do with a stack, right? It's so simple. It's a straightforward data structure. What can we do with it? What can't we do with it? And where's that boundary line? And why is that boundary line there? Computer scientists are obsessed with those types of things. We're not really going to dig deep into that in 162. But inevitably, when someone is saying, yeah, but a stack is really not as general purpose as a list, we know, but that's kind of the point. So we've got these data structures, and you'll notice that when I've mentioned these data structures, we're all aware of what they are. Okay? We know what a queue is. We know what the idea of a tree is. We know what the idea of a graph is, right? Even though we haven't really learned about it, but you can kind of get a sense of, we have this data, we have these things, these entities, and we want to show some relationships between them. We know what it is. But we don't know how, like, we're going to implement all these things in Java, not a graph, but we're going to implement these things. But we haven't talked about how we implement them yet, but we know what they are. Knowing the what and knowing the how, obviously they go together, but they're separate things. You all knew you all knew what a list was in Python, right? You didn't know how it was implemented, but that didn't matter at all. You knew what you could do, you knew how to use it, but you didn't know how it was built. You didn't know how it was implemented, and that didn't matter. That's a boundary line. The what is like how we interface with that thing. The how is how it's actually implemented. And we're going to like to talk about things on both sides of that line. When we're implementing these things, like we're going to implement a stack, obviously we're going to look at the how, and we're also going to look at the what, and we're going to be aware when we implement, what do they want to actually do with this stack. But think back to the list. Often when you're programming, you load up your programming language's standard library and you start using lists. And I don't care about the how, I just care about the what. And that's a good thing. We like that. That facilitates abstraction. I don't need to know anything about how my car works to use it. I don't need to know anything about how my HVAC system works in order to use my thermostat. I don't need to know what I don't care about. As long as I can use it to solve the problem that I have that tool for, I'm happy. And that's facilitating abstraction. And we all like to operate at a fairly high level of abstraction. No one in here is thinking about ion pumps firing when they move their hands. No one's thinking about neurons firing in their brains when they're moving their hands. No, they just move their hands. We operate at a very high level of abstraction. Remember last semester I said, tell the person next to you how to make spaghetti. And if you're dealing at a fairly high level of abstraction that another human being could operate in, get some water, put it to boil, add some salt, add your pasta, wait 10 minutes, you're done, right? Like that's basically it. But if I wanted to be a stickler and I said, no, how do you boil water? And you're like, okay, well, you get a pot. Well, how did you get the pot? Okay, well, you go walk over. Well, where's the pot? I could play this game forever. We could play this game all the way down until we get to some atomic units of work or something. But of course, we're not operating there. We're operating here, right? And think about it. Someone who's never cooked before, someone who's familiar with cooking, I can explain to make pasta pretty straightforward, right? I could operate at this level of abstraction. But someone who hasn't cooked before, I don't have to operate down there. I can operate probably maybe a little bit more here. I need to give them a little bit more detail, right? But that's fine. It's all about where we are in those layers of abstraction. And these data structures are another thing that help us with this abstraction. This has been such a common theme, even back in 161, and it's going to continue to be a common theme as we go and continue learning more computer science. We learned about functions. They facilitate abstraction. We learned about classes. We facilitate abstraction with that. Now we're building specialized tools that help facilitate abstraction. It's a lot of that. And we keep building on layers and layers and layers and layers. You go back 100 years and you were writing programs for computers, you were flipping literal switches to mean zeros and ones. You had to operate and interact with your computer at a very low level of abstraction. Then they made it better. We had things like punch cards, which were still terrible. Then we had like assembly languages. We had machine language, then we went to assembly languages, and then we had low-level programming languages, and then we have like mid and high-level programming languages like Java that make it so much easier to write code. No one in here is going flipping zeros and ones on their computers. That's a very low level of abstraction. We keep building layers and layers and layers and layers to make it easier for us, because we, as humans, like to operate at a pretty high level of abstraction. Layering, yeah. Data structures, okay. So a data structure is an actual implementation of an abstract data type. So, and again, I've said this before, although we have these things that are well defined, computer scientists are pretty bad and loosey-goosey with some of this language. I'll be as precise as I can, but be aware that I might make a mistake, and when you go reading online, chances are people might flip the terminology, but as long as you understand the context, you'll be fine. An abstract data type is like a stack. An actual data structure is some implementation of the stack, of a stack. So like the actual code, and when you're using it. FYI. So using the contact list, the what would be, well, it keeps track of friends, add and removes friends, we can retrieve a specific friend, etc. The how was, well, we used an array to store the friend objects. A linear search was done to check if a given friend was in the contact list, right? So there's the difference between the what and the how. Think of, in here, This is the how, right? This is more of the what. The what is what I can do with it. The how is, well, how the hell do I actually do? Like, how is that actually done? When we were dealing with lists, you never looked at this side of it. You never looked at the code inside the list class in Python. You only interfaced with the list. You only created them, appended them, removed from them, etc. Yeah, the warning. People will mix this up all the time. Any questions about any of that? All right, I get it. I beat the dead horse. Okay. So, the first thing we're going to actually talk about in terms of the data structures we're going to build and use is a stack. A stack is a straightforward example of a simple data structure. All of the action that happens on the stack happens at one end. Think of a pile of plates. Yeah, I think I always use that example. You ever been to a buffet where there's that stack of plates? Yeah? No? Maybe? I'm seeing a lot of blank faces. I don't know. Maybe you don't. Imagine a pile of plates. All right? And you come along and you want to get a plate. Right? The pile starts here, goes to here. And you want to grab a plate. Where are you going to grab the plate from? If you're not psycho, you're grabbing it from the top. Only a weirdo would be like, I want this one, right? No, you take from the top. And when someone comes back with a clean plate, where are they going to put it? On this giant pile of very heavy plates. Where are they going to put it? On the top. All of the action happens at one end. There's two ends. There's like a bottom of the stack and the top of the stack. But all of the adding and removing is happening at one end of the stack. That's a stack. And you're actually familiar with stacks. You've been using them not only on the computer, whenever you're using the computer, stacks are everywhere, but you have a mental stack that you keep track of things with. Stacks are everywhere, right? You ever have that back button on that, the back button on your browser? It's a stack. The last thing you were on was on the top of the stack. You hit back, well now you're there. You hit back again, well it's the thing below it. Thing below it. You go to a new website, oh, you add it to the stack, add it to the stack. Go back, go back, go back. Undo in your text editor, it's a stack. Like, you ever notice you can kind of, you make a change, you make a change, you make a change, you make a change. You don't like that change, so you go back, maybe you go back. You make a change, you make a change, you make a change, you go back, you go back, you go back, and so on. You kind of have these like diverging paths that you could take, but you're only ever really on like one path. But like you can go down one route, you make some changes, you come back to some point in time, make more changes, and so on. That's a stack. You've ever had some task you're doing and you get interrupted, you have to go do something else, and you get interrupted again? And then you get interrupted again, you got to help someone with their, making coffee. Then you go back to what you were doing, then you finally finish that, so you can go back and do that. You ever been writing code? And you're like, okay, well, I need to write code to do this. And then you're like, crap, I can't finish that function until I actually write this other function. In order to do that, next thing you know, you're like, I could make a whole new class to do that. Okay, then I can do a whole new class, and then with that class, I can then implement this function even easier. And once that's implemented, I can go back and implement this thing. That's your mental stack. That you use a stack everywhere, every day. I'm not being silly. This is like a well-formalized thing. Stacks are everywhere. Deal with it. So you're already all familiar with a stack. So we are going to define the stack formally, for lack of a better term. We're going to say, okay, this is what we want to do with our stack. And then once we've defined our stack, the what, we will go think about how we will actually build it such that it can do the what that we want. So stacks are a linear collection of elements. Okay, and actually before I just start reading this, questions. All right, stacks are a linear collection of elements, and all the adding and removing happens at the top of the stack. That is the word we're going to use, the top. All elements are pushed. This is a word we often use in the definition of stacks, if you go to Wikipedia. You push things onto the stack when you add them. It's called pushing. And when you remove them, we use the word popping. So you push data onto the stack, that's adding. Removing is popping. You're eliminating them. You're popping them off the stack. And people will use this phrase, it's last in, first out. The last thing that I've ever added, I've got a stack, I'm adding and removing. You've got your back button on your computer. You browse, you've gone from website to website to website to website. The last thing you were at is at the top of the stack. So if you were to hit back, that's the first thing you get back. The last thing you add is the first thing you'd get back. The first thing you ever added will be the last thing you ever get back. It's at the bottom of the stack. So here, whoop. Strange. So there we go. We got a stack. If this is the top of the stack and I want to add this new turquoise, that's turquoise, right? Sure, yeah. We add it, well, that's now the top of the stack. The top is changed. And if we pop the turquoise thing off the stack, well, now the thing below is the new top. I might be overkill. This might be overkill. You might be like, yeah, no, I get it. So that's good if you understand it. So what do we want our stack to do? In general, for all of our collections, they're all going to follow the same general idea. We want a way to add something to the collection, following the rules of the definition of the collection. We want a way to remove stuff from the collection, following the rules of the definition of how it works. We want to be able to look at something but not remove it. Basically, look at the top of the stack, but leave it there. Don't actually eliminate it, just look at it. Check if it's empty and tell me how many things are currently there. We could add a few more, fine, but this is your typical, this is what you need to have a stack. Add, remove, look at the thing, get the size, and check if it's empty. 5 key things. And then we're going to add the extra things that we usually do in Java, like our toString, our equals, our hash code, fine. But what we want the stack to do is add, which we call push, remove, pop, look at the thing at top, but don't remove it, that's called peek, get the size and check if it's empty. If at any point in time you say, well, why don't I add a method to like remove the second thing in the stack? What if I really want to remove the second thing in the stack? Well, that's not the definition of the stack we just created. So it sounds like you want something that's not a stack for your problem. But I really want to do it. Then go ahead, but it's not a stack. The definition of a stack is all the action ever happens at the top. And then people always want to get in this argument, but what if I really wanted to? Go ahead and make it, just don't call it a stack, because it ain't a stack. The definition of the stack is all the action happens at the top. So push, this is adding something to the collection. The element added will be the new top. Pop, remove an element from the collection. The removed element will be from the top of the stack. The element after the removed element will be the new top. If it exists, it's possible that there's only one thing on the stack, right? And if I remove it, now it's just empty. And this is a key thing. The removed element is actually returned. An interesting point here is in general, in Java and many languages, your add and remove return a Boolean to tell you the success. Remember like the contact list I told you, like if we try to add something, well, it always returns true because we can add. If we try to remove something that's not there, just return false. Interestingly, as a consequence of just the nuance and how the stack and the queue and et cetera will work, our general, our push, our adds, our removes will actually return the specific element, not a Boolean. So it's a little different, but inconsequential, really. Peek returns the element at the stack on top of the stack, but leaves it on the stack. And peeking does not alter the stack in any way. I know throughout 161 and 162, I've pushed making everything immutable. We don't want our data to have states. We don't want to be able to mutate the data, change something about the data. But when we have something like a stack or in general like a data structure, we could implement these things such that they're immutable, we could, but generally all of this stuff is very stateful. When I add something to the stack is different now. I've modified that stack. There's something new there. When I remove something from it, there's something, it's different now. So it is stateful. You will notice, for example, on assignment 1, if you looked at the country catalog tests, there were a lot of tests, right? Testing anything stateful is a pain in the ass. So you need a lot of tests for stuff like that. When you looked at the simple class, like the country catalog, or the country class, what was there, like 6 tests? That's easy to test. Like something that's stateful, whoa, it's a pain in the ass. Collections are notoriously challenging to test. That said, I have like a pattern to follow for making tests for collections that make it kind of, it makes it easier, I think, but it's in the eye of the beholder. So yeah, note, it is against the definition of a stack to add or remove or access anything from anywhere other than the top. And again, some asshole's going to say, but what if I want to? Then go ahead, but it's not a stack. It's not. You're breaking the definition of a stack. So the above describes what a stack is, but at no point did I mention how we're going to implement it. And that's intentional. We want to separate the what from the how. What we can do, what we want to do with our stacks, and how we're actually going to enable that to happen are separate things. Obviously, they're linked together in the implementation, but we do want to keep them mentally separated. In fact, in programming, we define a special boundary between the what and the how. Listen up, this is important. There's a special boundary, and that boundary is called the interface. Okay? And we are going to define an interface for our stack. And what's interesting is all of this definition of a stack, it's just the definition of a stack. It had nothing to do with Java. It has nothing to do with Python, C, C++. It has nothing to do with any of these other languages. It has nothing to do with any language. It's just an idea. It's just a mathematical idea, really. It's some definition of something. So, an example, do I have an example of the, yeah, here we go. Perfect. So let's say I have this little maze, right? Each little block we call like a cell, a spot, whatever. The black blocks are walls. The green block is where I'm going to start, and the red block is where I want to end. And I say solve this maze. A human can go like, well, yeah, okay, great. But you're writing some code to do it. How are we going to do it? Well, a stack is commonly used in this situation because there's a very simple algorithm for solving a maze if there's no cycles in it. Cycle meaning, never mind. Cycle means like, it's possible to loop back on itself. And you can like take a moment and think about the back button on your computer, right? Or the undo, right? You make this change, you don't like it, you hit undo. You make this change, 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 you make this change. I don't like it. Undo, 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 undo. I make this change. See how like there's a branch there? I can undo and carry on in another path. That's the idea we're going to go for here. So we want to find a path through the maze with something that we call a depth-first search. This is, a depth-first search is a very primitive, simple form of artificial intelligence. Look, it's no ChatGPT, but it is a form of AI, a depth-first search. Here's the idea. Pick a path not yet visited. Keep traveling down that path until the end or a dead end is found. If I follow down a path and I get to the end, I'm done. If I get to a dead end, all right, what do? If the end is found, we're done. If it's a dead end, we're going to backtrack until there's another branching path and then go down that path and just repeat this process. That's the whole idea. The backtracking is 100% dealt with by the stack. If we didn't have a stack, there's a lot of complex things we have to keep track of. But if we have this magic idea of a stack, here's how the algorithm goes. We add the start of the maze to the stack. Envision a stack right here that has the start of the maze. Right? Well, the stack is not empty. Get the top of the stack with a peak. So don't remove it, leave it there. I could remove it and put it back. It's the same diff. But look at the top of the stack. If the top of the stack is the ending cell, we're done. Obviously, at the start, we're probably not at the end. But you look at the top of the stack, are we done? If we are, we're done. Otherwise, if I look at that cell, the cell knows what neighbors it has. So I look at the cell and I'd be like, okay, do you have an unvisited neighbor? If you do, push it onto the stack. If there is no visitable neighbor, pop it from the stack. That's the idea. This might be hard to wrap your head around when you think of the initial state, but let's go through this. If the loop ever exits because of an empty stack, there is no solution. So here we go. Hold on. I'm going to click this to see if we can get it to restart. So there we go. Push it. Okay, it's got a neighbor. Oh, pop, push, 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 push. No neighbor, pop, no neighbor, pop, no neighbor, pop, no neighbor, pop, no neighbor. A valid neighbor. Push, 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 push. Now, you might say, why didn't it go down that path? And it's entirely arbitrary. When we write the code to do this, we're going to have a systematic set of rules where I'm going to say, oh, check up first. If I've got 4 neighbors, which way do I go, right? Well, we're going to want it to, it's going to be deterministic. Every time it'll follow a pattern. The pattern I followed was go north, then east, south, and west. That was my pattern, right? So that's why, okay, we go there. And that's why we went east before going south there. And that's why I went east instead of going west, just because I happened to go that way. I could have done it in a different order and the pattern would have been different, but it still would have found the end of the maze. All of that backtracking is just, it's all done by the stack. The stack takes care of all of that for us. In fact, when looking at this algorithm here, like this pseudocode, and for those of you that don't know, pseudocode is just a word to be like that's not Java, it's not really code, but it's kind of like code. It's a great way to describe an algorithm, right, I think. Somewhere kind of like between English and code. So none of this depends on me knowing how a stack works. Sorry, how it's actually implemented. We know what we can do with the stack. We know how we know what it does in terms of the last thing I put on is the first thing I get out. We know that property of it, but I didn't need to know anything about how it does what it does in order to solve a maze with this stack. Is that clear? If it's not 100% clear, right now what I'm really trying to emphasize is that boundary of that interface, the what and the how. With only knowing the what, I was able to describe this maze-solving algorithm. It's not important that you fully understand this maze-solving algorithm right now. Go, if you're struggling with it, just work through this with the example, and it's like a 1-for-1. Questions? All right, Try to see where the push, pop, and peek happens. Well, I kind of spoiled it because I just kept saying push, pop, etc. All right, so the interface. There are a lot of different ways you could implement a stack. But there's still only one definition of a stack. We only need one interface to describe what a stack is. And I don't give a shit how it's implemented. As long as it's correct and it implements the interface, then I have a stack. So what we can do is we can define what a stack is with an interface. Okay? There's a boundary right here. We've got this thing called an interface. And it tells me what I can do with the stack. It's going to tell me I can push, pop, peek, is empty, size, toString equals, etc. Hash code. Right? That's what a stack is. Then the implementations are going to implement that definition. It's going to implement the interface. And if I have any code that implements the interface, I have a stack. Now, the interface can't guarantee that the implementation is correct. All it can do is that it implements all of the things required by the interface. I'm going to show you concrete examples very soon. But the interface is this definition of what a stack is. And if I have a stack, I have a stack. I can use it as a stack. All right, so there are many possible ways one can implement a stack. All implementations must be a stack. They must follow the definition of what a stack is. In Java, we can create an interface that defines what operation a stack is. If someone wants to implement the how of a stack, they implement the interface. I'm just reiterating what I just said. Ultimately, the interface is simply a list of abstract methods. An abstract method is basically just the signature of a method. There's no implementation. I'll just show you an example. There. That's an interface for a stack. Notice, I'm going to show you the actual interface we've got. I'm going to open up the actual interface I give you. It's basically the same as what I just showed you, but it includes java.comments. So I'm going to go in here, stack. First, you'll even notice it's got a little different color here. It's not a C, it's an I, and it's green. It's not blue. So here is the interface. There's a lot of comments in here, but that's because the comments are describing what it is. That top one is telling me what a stack is. This right here is the signature for a method called push. And the Java docs above it describe what push is. So all the documentation here is just using English to describe what the hell a stack is. All of the code, well, like there basically isn't any. There's hardly any. All of the code, this is what the code is. If I eliminate all of the Java doc, that's what I'm left with. And you'll notice it's not public class stack. It's public interface stack. And that just tells Java, this isn't a class, this is just an interface. There's going to be no implementation in here. It's just going to be effectively a list of methods. That's it. There's no constructor, because you can't make an instance of an interface. You can't do it. So there's no constructor. All it is a list of the methods that we want this class to have, with no implementation. You'll notice that they don't say public Boolean push. Adding public here is kind of like, you could do it, it doesn't really matter. But the reason I don't say like public Boolean push, public T top, public T peak, public Boolean is empty, we don't add public there because an interface by definition must be public. It's that boundary, it's the definition of what you can do, so everything's public, it's public. And the name of the interface is stack. We can push an element, we can pop, peek, is empty, and size. But you may have noticed something interesting. What do you notice about this that's a little new? It should be obvious. Someone say something, please. Well, there is no actual code, that's true, but that's not what I'm getting at here. What the hell's that T? Shh, shh. Don't cheat. That T. So we got a bit of an issue. If I wanted to have a stack of strings, right? What would be the type of the elements I'm pushing onto the stack? Strings. What would be the type of the element I'm popping from the stack? Strings. Great. So I can write an implementation for strings on a stack. And then someone comes along and they go like, okay, great, now make a stack for integers. And you're like, okay, so now I need to re-implement it, but now the type of element I'm pushing on the stack is integer. And the type of element I'm going to return is integer. And then you come along and you're like, okay, great, now I need it for cell, like maze cells. All right, so I need to make a new stack where the type of the element is a cell. And then, so I'm going to be able to push a cell and return a cell. And then someone comes along and they say, okay, great, now make it for friends, and so on and so on and so on and so on. We got a bit of a problem here. So this is where generics come in. This is where we can say, okay, look, we have a stack of elements of some arbitrary type. That T, think of T as a variable for a type. That's what it is. So this is going to say, if T is a string, well, that means element is a string, pop returns a string. If T is an integer, now it's integers. T, this generics, is how I can make it even more general. So now I don't need to make a stack implementation for every possible type of things I want to put on the stack. No, I can define it once. And then when I create the stack, I can specify, okay, it's a stack, and I'm going to put strings on it. But the implementations don't need to change. It's pretty nice. It might throw you off a little bit at first once you get going, but once you use it a little bit, it'll probably you'll get pretty comfortable with it, I imagine. So generics, the use of T is something new and not an idea discussed yet. Now, we didn't really need generics in Python because types really didn't matter so much in Python. They mattered, but you were able to kind of like mix and match. It didn't matter, right? In Java, it matters. So yeah, imagine I wanted integers. So I'd have to write a push for integers, a pop for integers. Then maybe someone else wants to make one for strings. Same thing, friends, same things, right? So there has to be a better way. There is. It's generics. So here's an example. Now you're going to, I'm jumping ahead a couple of lectures with this particular example code, but so like you're going to see array stack, and you're like, well, what's an array stack? We're just talking about a stack. I know. We'll get there. But this is how I can say I want to make a stack of integers. So I specify when I'm creating it what the type is in those triangle brackets, the less than and greater than symbols. Cool? Cool. So I only actually ever have to implement it once, and then when it gets run, it's like, well, that t is a string, or integers, or whatever it is, depending on what I need for what I'm using it for. Yeah, When creating an instance, we specify the type between those symbols. In the above example, with the use of generics, 3 different stacks are created, each with different types. You'll notice here, I included it here in general. We actually don't need to include it on the creation side. It's smart enough to know. It doesn't matter so much. Now, and the last warning, it's not possible because everything that's a class, because every object you ever make inherits, whether you like it or not, inherits from the object class. Okay? Not objects. Objects is full of static methods, right? Object class is at the top of the hierarchy. Everything you ever make is an object. And every object, whether you implement it or not, whether you override them or not, has an equals, a toString, a hash code, etc., a bunch of methods you get for free. Often we overwrite them with what we need them to do. We make a more helpful toString, for example, like we've seen. But if I don't do that, I still get them. And in order for generics to work properly, there needs to be some consistency with, well, all things on the stack have to be able to do X, Y, Z. Equals, toString, hash code. All of those things have to be there. So that's why, whether you like it or not, every class is an object. But that creates an issue for primitive types, because primitive types don't have things like dot equals, like your int, your double. So what we do is, well, probably the most simple solution possible is we'll just make a class version of that type. So if you want to make an object version of an int, you make an integer, uppercase I. See, it's following that pattern. All classes start with an uppercase letter. You want the object version of a double? Well, it's double, but with an uppercase D. You want a Boolean? It's Boolean with an uppercase B. So that's how you can get the class version, the object version of primitive types. And if you wanted to use generics with primitive types, you can't. You just use the object version of those primitive types and you're good to go. So you can't have a stack of ints, but you can have a stack of integers, which is effectively a stack of ints. Yeah? No? Weird? You'll see. Questions, questions, questions? No questions? No nothing? So we look at this. This is just the interface. It tells me what. There is no how. I can't make an instance of a stack. I can't do it. We need to tell Java, we need to write a class for a stack. But, I mean, now that we've defined the what, we actually have to answer the question, okay, how are we actually going to implement it? I made a big to-do about separating the what and the how. Now it's time to talk about how. So how are we going to implement this stack? Well, we need a place to store the data. And, well, as of right now, we really only are aware of one tool. We really only have one tool in our toolbox that's good for storing data. It's an array, right? I'll have a stack, and I'll store the elements in an array. That's how I'll actually implement the stack. Okay? Now, how are we going to do it? Well, so arrays are great for storing contiguous data, right? An array of size 10, storing only 6 elements though, 0 through 5, right? So if we use an array to store data on the stack, how should we keep track of the top of the stack? If we make the top of the stack index 0, well, there's a huge pro to that, in that I always know where the top of the stack is. It's index 0, right? I don't care where it is. It's always at index, it's at index 0. But the con is, if I want to push something onto this stack, and if I push something onto the stack, it's going to become the new top, right? Or at least it has to in order to follow the definition. So I want it to be the new top, so it must go to index 0. So something's already in index 0, the current top. I want to add a new top. So I would have to move everything down one, right? I'd have to shuffle everything down one spot in the array to make room for the new top. Then, if I wanted to remove something, if I wanted to pop from the stack, okay, great, I removed the thing at index 0. That was easy. But now we've got an empty spot at index 0, so we have to move everyone down one. Not a huge deal, not a huge problem, but every time we add something, that's going to be a linear time operation. If there's n things in the stack and I want to add another one, how many things do I have to move to make room? N. If I have 2n things, I have to move twice as much things, 2n. So every add and every remove is linear. What I could do is always make the top the other end. If I wanted to push something to the stack, we'll just add it to the next available spot. Pop, remove it at the last spot. But we need to keep track of where the top currently is. But if you remember from our contact list, remember how size, the number of things in the array, also corresponds to like the next empty spot? It's kind of handy. We'll pick up here tomorrow.